proximity tracing. When I actually turned in this talk, that was actually quite a new topic, and not a lot of people had actually talked a lot about proximity tracing, but now it seems to be on everybody's mind, considering that Germany's just published its own proximity tracing app 2 days ago. And I want to have a little look at what we're trying to do, why we're trying to do it, and whether it's actually something that we as IT security people can support, and whether it has actually been done properly in order to not put anyone's data at risk. So let's start with the actual problem. We're currently in the middle of a pandemic, and there's really only two ways to contain a pandemic. You can either do a hard lockdown, everybody goes home, everybody stays home and starts washing their hands. And at that point, the virus can't really go anywhere. Nobody's meeting anybody, everybody's keeping a very good hygiene, and that will, of course, drown out the virus, but the costs are really super high because nobody can do their work, or many people cannot do their work. The kids are home, everybody's distracted, the economy is crashing, and of course we can't really have fun. We can't hang out, we can't go to bars or clubs or dancing or swimming or rock climbing or whatever it is. And so we don't really want to do that. The one other way to contain a pandemic is contact tracing. Now, if contact tracing works out right, it can actually be done with very little impact to the public. What we do is we basically try to find the people who are infected. They report themselves when they have symptoms. We test them, and when they test positive, we ask them, well, which people did you meet in the last 2 weeks? And we just put all those people into quarantine. And then we wait 2 weeks, and anybody who's not positive after those 2 weeks gets to go out of quarantine, and anybody who turns positive will then again trace their contacts, and thus we'll be able to hopefully contain and mitigate most of the contact between people without having everybody stay home. The whole problem with this, it's labor intensive and very slow. We can only do a couple hundred cases every day before we just run out of humans to do the contact tracing, and it takes some time. I mean, it'll take about 8 days for people to even have symptoms, and then they gotta come in, they gotta get tested. Then you gotta ask them, like, who did you meet? The people might not be able to remember everybody they met, and until you've figured out most of the contacts, there's 10, 11, 12 days gone past, and since you're already infectious 4 days after contact, that's a big problem, because the people that person was in contact with could already have infected people that are already infectious again themselves. So then we got to trace contacts of contacts, and that very soon becomes really impossible to do manually. So really the only solution, if we want to do this with high effectiveness, is automated. And the solution to that, the solution that has established itself over the last couple months, is Bluetooth beacons. We've probably all heard of Bluetooth beacons. They're used for all kinds of short communication. So for instance, if you lose your little Bluetooth in-ear headphones and you pull up the little app that tells you that they're right there on your bed, you silly thing, right? Those things, that's all Bluetooth beaconing, right? The headphones are just continuously shouting out to the phone, hey, I'm here, and the phone can just tell by how loud it is, how close the phone is to the actual beaconing, and using that you can actually get relative location very accurately, actually more accurately than commodity GPS. And so Bluetooth beacons seem to be the ideal solution here, because it's widely available, right? It can be used on any phone that has Bluetooth Low Energy, which is pretty widely deployed at this point. It is much more accurate than cell tower location, and it is much less invasive than some of the other methods that were proposed, like for instance ultrasonic, which could potentially be more accurate than Bluetooth beaconing. But do you really want to download an app from your state that as a first thing asks for unfettered access to your microphone 24/7? No, you don't, right? So nobody's really gonna install that. And Bluetooth beacons are the perfect middle ground. As we're gonna see, they can be deployed with relatively little impact on privacy, but at the same time, we can get pretty good data out of them. So how does that work from a user's perspective? It's actually pretty simple. If you meet somebody, your phone will send keys to their phone, and their phone will send keys to your phone, and both phones will just remember the keys. And then if the other person gets tested positive a couple days later, these keys can be sent to a server and then transmitted over the internet to all other phones. And then your phone can check with all of the published keys, have I seen any of those? And if it has seen one of those keys that has been tested positive, then it can send you an alert, and you can get it tested, and then potentially, if you're tested positive, again, your phone will publish your keys to alert further on down the chain. So when I first proposed this talk, it was supposed to be about PEP PT and DP3T, which are two efforts to make such a protocol that are at this point no longer really relevant, so I'm just going to touch on them for a short moment. PEP PT was the Pan-European Privacy Preserving Proximity Tracing, which I don't know who came up with that name, but it's great. It's a centralized protocol, and it's initially what German politicians wanted to deploy here. It's still the approach favored by France, but it's a centralized protocol. All the data is in the cloud. And we don't really want that, because the person who controls the cloud can probably, trace contacts between any two people at any time, and there's no way for you with the phone to tell. So really, the data should stay with you until you're tested positive, so that you can be sure that your data isn't used for anything else. And that was the approach favored by DP3T, which was originally developed by EPFL in Lausanne and ETHZ in Zurich. And they split off from PEP PT to make a decentralized proximity tracing protocol. And that's also the father of the protocol that's gonna actually be widely deployed now, which is the exposure notification. Yes? So South Korea is an interesting example, because they had an app very, very early, and by then the phones didn't really support any of those APIs yet, so they had to actually rely on cell tower location, if I'm informed correctly, but I'm not quite sure. France, they're not currently using anything, at least last I checked, but they do want to deploy PEP PT because it gives them a more centralized and thus more powerful data source. But the difficulty with that is that Apple has just said, nope, not on our phones, and so they kind of have the problem that the app can't really work on iPhones, and that's a pretty big roadblock. I have no idea how China automates these things. I'm not even sure China needs to automate these things. I know that Thailand, they built some sort of automation, and then they later published that it didn't help them anything, but that was mainly because by the time they were done developing it, they were also done with the virus, and they no longer had a problem and could just trace everything manually. The standard that's going to be in use now is a joint development by Apple and Google, which, by the way, is really something they're pushing hard. This joint Apple Google logo is just appearing everywhere right now because they seem to really want to push their brand as something as associated with privacy. And it is called the Exposure Notification API. It was originally called Privacy Preserving Proximity Tracing, but that name was changed for political reasons. Basically, proximity tracing sounds really negative and like you're giving up your data, while exposure notification, who wouldn't want to be notified of an exposure, right? So that's basically just putting a little bit of lipstick on the pig here. And there's been a few other name changes throughout the spec that you have to keep track of. If you're looking at earlier points in the spec, you'll see things like Bluetooth advertisements, and all those things have been changed and renamed mainly because people who do not usually look at protocols like this looked at these protocols and started tweeting things like, oh my god, I can't believe that they're using this to show us advertisements, which is of course a gross misunderstanding of what a Bluetooth advertisement is. So Google and Apple scrubbed all these things from the protocol. This is the current de facto standard, mainly because, well, it's the only thing that works on iPhone, and Apple's not going to let anything else fly. And it has an incredibly low privacy footprint. No personally identifying information leaves your device, and until an exposure actually occurs, that stays that way. Only when you get tested positive is there any sort of privacy footprint. In theory, of course, the protocol allows discovering that there is a phone nearby, which of course that's more information than none, but that's already possible without that protocol. I've held a talk about that a while ago here called Snoopy NG. If you want to know about those things, you can probably find the slides in the GitHub. So I'm going to go real short about how this protocol works because it's actually really pretty simple. Say you have a phone. You're Alice, you have a phone, and your phone now picks a random key, any key, and that's called the daily key, and it's valid for 24 hours. And now it uses an algorithm called HKDF to generate a temporary key. So there's basically that's basically an algorithm that will allow you to take the one random key you made and generate 96 keys, one for every 15 minutes. And those 96 keys, when you start with the same daily key, you will get the same 96 keys. But if you only see one of those 96 keys, you cannot tell what other keys are associated with that. So it's anonymous at that point. And then it uses that it sends out that key to the other phones, and it sends along a bunch of metadata like how loud the beacon was sent and things like that. But that metadata is AES encrypted and can only be decrypted once your key material is published, because it uses this AEM key and this oh god just a second. And this AEM key is not available to you, so you will only be able to generate this AEM key of your own once you have the temporary exposure key, and thus you cannot actually read any of that metadata that's sent along unless an exposure takes place. Now, when an exposure takes place, what happens is really, really simple. You have those daily keys, and your phone keeps a log of them. And when you're tested positively, it will take the last 14 daily keys and publish them to the cloud. And now every other phone downloads your 14 keys, and it'll actually generate your temporary exposure keys from each of these keys, and it can then check to see whether it has seen that key and if it has seen that key, it can actually decrypt the metadata and actually generate accurate exposure information. Now, that's a really pretty simple protocol, but it keeps a really low privacy footprint, because there's not much information that you get about a particular phone, because anything you get from the phone is actually just, well, or indistinguishable from random data until you have those daily keys that get published. Now, going on, we have the Corona warning app in Germany, which is an implementation of this standard. So the standard itself is, of course, part of the operating system. Yeah. It's super trivial, but there's also so many tiny little things that can go wrong. So, for instance, in the very beginning, that metadata was actually not encrypted, and that allowed you to get certain things out of it. Also, there was a problem where the daily exposure keys, they would actually get generated from one master key, and they had some idea for allowing like larger chunks, like thinking into the future if you want to use this for maybe a different pandemic or something, and that turned out to be a problem in some edge cases, so they dropped that. And then there's also another thing where the server, in the beginning, it wasn't required to actually shuffle the keys. So when you publish your keys, that's a batch of 14 keys, and those stay together because the server was not required to shuffle those. And so if somebody was tested positive, you could tell they're the same person on multiple days, which is also a slight privacy invasion. And so they went through all these iterations to make sure that every little thing got ironed out, and that just took a while. But it's also been available for a while. That was actually published with iOS 13.5, and I'm not quite sure when Google actually published it. But so these things have been available for a couple weeks. But then, of course, an app had to be developed around that, and that took another 6 weeks to develop the app and the server infrastructure and the backend and the communication with the laboratories and all those things that you also need to keep this going, which is the next thing I'm gonna get to. Yeah. So now this, yeah. Um, Actually, the contrary is true. The app does not have access to that key material. So this entire thing happens in the operating system, and the app only gets to see a high-level API for this. And so all of those keys are controlled by the operating system, and the app does not actually get to see them unless it signals an exposure. And of course, you get your prompts for allowing things directly from the operating system, so you can tell when those calls into the operating system are taking place for taking this data out. So you can make sure that you don't really have to trust the app unless you get tested positive, in which case the app gets all the data. Um, as long as you trust your actual operating system. So of course you gotta trust Google or Apple, depending on what sort of device you own. But the app actually has very little access to that key material. So this is of course only a tiny part of what has to happen, right? That's just sending out the keys and receiving the keys, but you need like a whole massive app ecosystem to like support the backend of that. And for this, every country is currently building their own app, which is also the biggest shortfall of this approach, because we will eventually need some sort of roaming to allow, for example, a German in France to get a notification if they were close to somebody in France, or, which is a really hard to get edge case, if you are meeting a Frenchman in Italy, right? You still want to be able to get a notification if that Frenchman that was in Italy at the same time as you were later gets tested positive. So we will eventually need some sort of at least Europe-wide roaming, but that has not yet been developed, and every country is just slowly rolling out their own infrastructure that is luckily largely compatible because they're all using that same basic exposure notifications API, but we're not yet to a point where we can share data. Now, this Corona Warn app, yeah. So I've seen somebody doing a back of the envelope calculation that said it might be possible to do it Europe-wide, but certainly not worldwide. The data involved is not super large, right? You get 14 keys per person that is tested positive, so that's not a lot. You can do that Europe-wide, but once it goes much beyond that, just the amount of computing time required on your device to generate all those short-lived keys to test them all is just getting too much, and it's going to be a drain on your battery. So if we want something that works larger than Europe, we'll certainly need a different concept for that. And the current idea for that is that your phone could just like tell in which country it is, so that your phone, when it leaves Germany and it goes to, let's say, Italy, it would automatically talk to an Italian server, and that of course requires some sort of geodata, but it only tells you what country that person is in, so it's not super personal, and it would allow making that whole process a lot more efficient. One problem with that is if you're, say, in the Dreiländereck, then you have the, huh? You have that problem that your phone's just constantly switching between countries, and that can, of course, lead to double countings or things not being counted at all, because you've got to make sure that the person you're standing next to is actually booked into the same country that you are. So we would ideally have really, really sharp borders, but you can't draw sharp borders without GPS, and you can't do GPS without, again, opening potential for leaking user data. So that's still really very much a problem that's being figured out right now. Now, our German app has been jointly developed by SAP and Telekom, and it's been available since the day before yesterday. And in retrospect, that's pretty unsurprising, those two companies, because SAP, as somebody said, they're just really, really good at writing apps that are basically just a database frontend. And Deutsche Telekom has lots of experience with setting up multi-million client deployments, and you can trust them to do that at scale, quickly, and without stumbling. So I guess it's should come as little surprise that those two companies were picked. Now, the user interface is pretty simple. All right, you download the app, and it asks you for permission to enable COVID-19 exposure logging, and you say sure, and it asks you to send you notifications, and you say sure, and then exposure logging is active. In that moment, your phone starts sending those keys, and the app will show your risk as unknown initially, and then in 2 weeks, hopefully everyone's app goes to green and says, well, there's no exposure. Now, I'm not going to lie, when I first heard SAP and Telecom are developing that app, my thought was, oh God, that's gonna be a disaster. Because I mean, I'm not exactly trusting those two companies with my personal data usually, and I figured they would just build a colossal proprietary app that nobody can audit, and we just have to trust those two that everything's safe and everything's perfect. But the transparency is surprisingly good. Um, I was actually astounded. They have put up a GitHub. They have their app on there. It's open source. They also have the server on there. It's open source. And there is documentation. It's written in Markdown. The issues are public, and they're accepting pull requests, which is like I was not expecting that much transparency. And in fact, there's a brilliant interview on Unsere kleine Welt, which is a German podcast that interviewed two developers from SAP that talked about how you go about in such a company developing this sort of awareness. And they're talking about how like they were starting to develop the app, and suddenly, just as it normally is, Word documents were flying around, and they were like, no, we need this for the documentation. This has got to be available for everyone. And everybody's like, so you mean we're supposed to export it as a PDF? And they're like, no, Jesus, no. And so it took a little while to get everyone on board with that, but the upshot is that now everything's Markdown, everything's open source. You can just go on GitHub, you can read it all. You can write an issue. There's people there that are going to answer you that take these issues very seriously. There's been issues raised over the last couple weeks, and minor things tweaked, and there's actually been pull requests from external people, and it's actually surprisingly nice. So enough praise for SAP. This is the architecture. It shouldn't really come as a surprise to anyone. There's nothing in here that's really unexpected. You, as the user of the app, have the app. The app scans and broadcasts, and you talk to your doctor, and the app talks to the backend, and your doctor talks to the backend, and that's basically it. Um, there's three parts to the backend. We're gonna get to that in a minute. So there's the Corona Warn app server, and there's a verification server. Now that split is meant to enhance privacy because one server has the key material and one server has health data, and those never get mixed, so that you can ensure that nobody can ever trace who that health data belongs to beyond what's obviously possible in the German medical system, which of course has your name and your address and your phone number and those things. And then there's the portal server, which is the only part of this app that's actually not open source. It's a pre-existing component developed by Telecom, which was initially meant to aid the communication between a laboratory and a doctor. So a laboratory would deliver its results to the portal server, and the doctor could pull the results from the portal server, and it would make the communication of medical data more secure and faster, so that your doctor could have your lab results quickly, and that your lab results wouldn't actually be in the mail, which comes with its privacy risks. And they now just modified that server to actually be able to use it to talk to millions of apps of end users to directly deliver the lab results to the users, instead of delivering the lab results to the doctor that then has to deliver them to you, so that those couple hours can be shaved off, and you can just be notified as soon as your lab results are available. Now here's the actual protocol, and this seems complex, and I hope it's actually readable, but it's not as bad as it looks, and I hope you can follow along. Oh, perfect. So basically this is, we're now just looking at the process of somebody who tests positive, because, well, We've already looked at the process of just sending and receiving keys. But if you test positive, you get a QR code and you sign up with that QR code. And that registers you with the verification server and you get a token. And then basically with that token, you keep polling for results. And whenever you poll the verification server for results, it in the backend polls that test result server, which is the closed source component I talked about. And most of the time you just get no result back until at some point a result arrives on the test result server and you get your positive test result back and you get a notification on your phone. Boom! You're tested positive. So now the app actually asks you, are you willing to share your diagnosis keys, which is a really important step, right? The app will never share your personally identifying information without asking first. And when you're saying, yeah, sure, you can share my diagnosis keys, the app assembles them, basically these 14 daily keys we've already talked about, and then it sends the registration token to the verification server again to get a TAN. Now that TAN is important because the verification server it knows your test results, but the Corona Warn app server, it's not supposed to know your test results. So basically all it knows, or all it can do is verify a TAN, but it never sees the actual test results and thus cannot associate people with it, which means it's no longer anonymous at this point, but it's at least pseudonymous. So now you have your TAN, and with that TAN you can upload your diagnosis keys, and the Corona Warn app server will then verify your TAN with the verification server, and the verification server can confirm, yes, that is actually a valid TAN, and you're allowed to store that set of keys in the database, and you'll get a success message back, of course. And now every once in a while, that Corona Warn app server, it will find data it has to actually publish, and it will pull that data from the database and upload it to some content delivery network, which is basically just like a really, really normal content delivery network. So you have like another phone from another person, and it can now download these diagnosis keys from the content delivery network, and then there's another phone and it downloads keys from the content delivery network, and then the checking goes on with the normal proximity tracing or exposure notification API with those keys that have been downloaded. So from there it's basically again the protocol that we've already spoken about earlier. Yes, that's correct. The PEP PT actually had a problem with that because the assembly happened on the server, not on the client. So that downloading the keys was unauthenticated was a huge DOS issue. And so they fixed that by saying, well, there's going to be a CAPTCHA there, which actually they put that literally in the protocol, show the user a CAPTCHA, which is really funny to me. But here this is not a problem because delivering those keys, that's basically just a static file that has to be delivered. It changes like once a day, and from there it can just be aggressively cached and be delivered at massive scale, and so it can just be completely unauthorized because all the actual compute time is used on the handset itself. It's HTTPS, and I have not tried pulling the data manually yet. I sadly didn't have the time, but as far as I understand the protocol, you should be able to just pull these keys with curl and just have them. However, well, those keys don't really give you anything, because unless you've seen any of those people, the keys mean absolutely nothing to you. Uh, so in order to tell how many people tested positive, you would count the keys, or what do you mean? Yeah, the keys on the CDN are actually for all of Germany. So if 100,000 people test positive in a single day, then there will be 1.4 million keys to download on that day. And all phones will pull these at a random time of day. Um, but like 14 million keys, if every key is like, I don't know, 4 kilobytes in size, I don't really know by heart, but that's like 60 megabytes. It's like, it's not a huge amount of data. Yes, that's actually, yeah, that's actually a shortcoming of the protocol that's also noted in the documentation. You're sending the keys for the last 2 weeks after you get a positive test result, but then you're not sending keys into the future until you get a negative test result. So if you run into somebody after you've already been tested positive, that is not actually mapped in the system and no alert will be generated. Um, that already takes us nicely into shortcomings of this system. One shortcoming I've already mentioned, but there's a few more problems with this. One thing is that in Bluetooth Low Energy, listening is actually pretty expensive. Transmitting, not so much. Your phone will send a broadcast 4 times a second all day, no problem, but it will only listen for 2 seconds every 5 minutes. So if somebody just walks by you quickly, 5 minute resolution, it's not going to show up. That means only contacts that are at least 5 minutes long will definitely be detected. Everything that's shorter than that is actually hit or miss, and only contacts that are at least 10 minutes long will actually be detected as a long contact, which is usually not a problem because a main way of transmission is people actually talking to each other for a while, so those 5 minutes work quite nicely. But if you just go up to somebody, you give them a quick hug, and you both walk away, it's probably not going to show up on the app at all. Um, and such a close contact will usually not be spotted. So it might actually be necessary to still interview people in order to spot close contacts. But usually, if you have hugged somebody, that will actually be somebody you remember. You probably know that person. We have 5 different scenarios here to illustrate that. So, device 1, super simple. Met on the streets, 3 minutes, kept their distance, detected by the app, everything's perfect. Device number 2, that's more of a problem. They meet each other. It's seen twice, so it's actually correctly identified as a long contact, but they've hugged each other in between, and the app cannot tell that because it only measures once every 5 minutes, and the chance that it's actually going to hit that very moment is super low. So that's something that's actually I've not detected by the app, and is not possible to detect that using Bluetooth Low Energy beaconing. Person 3 is missed entirely. They've stood together on the train platform for 2 minutes, and it's just never seen because contacts that are shorter than 5 minutes may be missed. This is not a huge problem because if you're just standing next to somebody on a train platform for 2 minutes, the likelihood that you're going to infect them is rather low, but it's important to keep in mind that these things cannot be identified by the app at all. Similarly, device number 4, they met. They met for 3 minutes. They actually hugged, but it's not detected because they meet here and they actually hug. You can see that the lines are really, really long because the amplitude of the signal is really, really high. Then the signal goes lower, they talk, but before the 2-second listen window starts, the other person already walks away and the contact is just entirely missed, even though it would have been pretty crucial to miss that contact because of the close personal relationship. And you really still have to rely on asking people whether any of those close contacts happens, because the app might miss those. On the other hand, you can get false positives. If we look at this person, so they only really were very close for like 1 second, but it happened to be that 1 second where the phone was listened, and so it's identified as a close contact, less than 5 minutes, but it's really just two people brushing by each other really, really quickly. So it's just a false positive. It doesn't actually amount to anything in real life, but the app sees it as rather high priority. That's also not a huge issue because false positives are much less bad than false negatives. We can actually follow up with quite a large amount of people, and we can actually deal with sending quite a large amount of people into a quarantine, even if that's not strictly necessary, as long as we don't have to send everybody home. But it is a thing to keep in mind that some of the people who are detected are going to be false positives, especially since the reporting time is 2 weeks, which is quite a long time period. To summarize, the app's actually pretty good. The question everyone's, of course, asking from this talk, the only question I really need to answer is, should you install this app? As an IT security professional, should you install this app? And as the headline already says, I think this app is as good as we could have hoped for. I was actually not expecting this project to go this well, and I was positively surprised. SAP are actually trying to meet a set of criteria that I've put here, and these criteria, they were put up right in the beginning before anybody even started developing on this app by the German C3. And they said there's got to be no central entity to trust, so there's got to be no central server that I got to trust to do things right. Everything's got to be on my device, where at least if I'm a little bit capable, I can like tell roughly what it's doing. We got to minimize data, so there's got to be no personal identifying information that is not absolutely necessary. It's got to be anonymous, which it is, as long as you haven't really been as long as you haven't been tested positive. And if you get tested positive, at least it falls back to pseudonymity, which is pretty much the best you can do, given that you actually have to notify people. And there is no central movement profiles. No place in the system are there any geo information, and even if the actual contacts are not stored centrally, so there's really no way to get a central movement profile, and the server will actually only keep the things that it has to publish on any given day. So as soon as people stop getting tested positive, that database will just shrink, and as soon as the pandemic is over, that server will automatically just be an empty web server with an empty database pushing no data at all to the CDN, and a CDN that's providing no data at all to the client. So it's a self-destructing system. As soon as its purpose is fulfilled, there's also no more data in the system, which is pretty cool. And it satisfies the criteria of unlinkability. So we can't link any person to their particular keys. We have no other information except that we saw a key, but we do not know who that is. That actually also limits the usefulness. We do not know when we met that person, because that, of course, would allow linkability, which means that there's certain things we just cannot tell, and it makes the whole thing less accurate, but at least we manage with the least amount of data we can have. And of course, the communication is unobservable. It's all SSL encrypted. Nobody can just eavesdrop on the communication between client and server, but I guess that's pretty much given at this point.